Hello everyone, welcome to all of you in my lecture today. So in today's lecture, I'm going to discuss about the parts of chemical reaction enzyme, which is newly added in the GATE chemical engineering topics, which is enzyme kinetics. Okay. So in this lecture, I will be going through the enzyme substrate complex formations reaction. That is, after derivation, we call it as a Micheli-Menten equations, and we'll discuss about the Micheli constant and the physical significance of the Micheli constant, and I will be also discussing about the graphs of miscellaneous equations in various forms, which is very important for the GATE examination point of view. And I will be also discussing about the various parameter which is involved in miscellaneous equations, which can be asked in the numerical in the GATE examination. So let's try to understand the topic. So the reaction here in this particular topic will involve the reaction of enzyme with this substrate, and it will form the enzyme substrate complex, that is the intermediate, and after that enzyme substrate complex get dissociated into the project, right? So generally we when we discuss about the enzyme, we do not have enough background about these particular enzyme and all, because we don't study all these particular topics in the chemical engineering topic. So I'm just giving you the basic definition of enzyme. The enzyme is a protease biocatalyst which catalyzes the biochemical reaction which is taking place in our body. So enzyme is a part types of a catalyst. Okay, that is a, we can call it as a bio catalyst, that you should remember, right? So this is a biocatalyst which is going to catalyze the biochemical reaction taking place in our body. So here I am writing catalyze biochemical reaction in our body. Okay, so in our body or in anybody in human living life, like, so here how which types of reaction will be happening. So this is substrate S will be reacting with this enzyme, and this reaction will be a reversible reaction, and it will be forming the enzyme substrate complex. Okay, generally we write it as a ES, that is ES, right? I will be going a little bit faster because we don't have that much time. ES star, that is enzyme substrate complex, and again it will get dissociate while forming product, and enzyme will be coming out, right? Because at the end of the reaction we are very interested in getting our product catalyst separation from the product, so that we can use again this catalyst for the reactant, right? So it's very important uh, things. That is the basics of chemical reaction enzyme. So here I am assuming the rate constant is K1, here the rate constant is K2, and here our rate constant is K3. So this is a call as substrate. This is our enzyme, and this is our enzyme substrate complex, right? This is our enzyme substrate complex. So it's very important. Now, from the basics of chemical reaction engineering, we all know that the rate of reaction. So R is getting reacted into with E and forming enzyme substrate complex. So I am writing the dissociation of RS. That is RS, uh, rate of reaction in terms of dissociation for S. That is equals to K1 concentration of S and concentration of E, right? And it is also getting formed for this by this reversible reaction minus K2 and concentration of ES star, right? I'm assuming that is equation first. Next is, if I am trying to write the rate with respect to ES star, that is equals to what? Uh, Rate with respect to ES star, that is equals to, uh, I am writing for the formations because this is plus, so that is equals to Q1 concentration of E, concentration of S, and it's getting dissociated by two reaction, that is this reaction and this reaction, right? So minus K2 concentration of ES star and minus K3 concentration of ES star, and here there will be a concentration of H2 because uh, here there will be presence of H2O also. So H2 will be present in excess amount. So I'm taking here that concentration also, because at the end of this derivation, we'll have to neglect all these things, because we'll have to apply the pseudo steady state approximation, where concentration of one, if concentration of one reactant is very high, then it will be constant. So that is RES. That I am assuming this is our equation second. And if we talk about total enzyme concentration, that is equals to E plus ES star. So can I write E concentration of E, that is equals to E total minus ES star. Okay, so I am assuming it is a equation third. I think up to this it's very clear to all of you. Only it's basic of chemical reaction that we study in various forms, right, for the various reactions. Now here, since this is RES, right? This RES is our intermediate. This is our intermediate. So from transition state theory, we can call it as at intermediate. The formation of intermediate is, it forms for a very less interval of time. So rate for the intermediate will be equals to zero, right? So I can write R ES star, that is equals to zero, and from there we will be able to calculate the value of this uh, concentration of intermediate, right? So the next slide I can write that is R ES star, that is equals to K1, and that is concentration, that is E total minus ES star minus K2 concentration of ES star, okay, minus K3 concentration of ES star into concentration of water, right? So one very important assumption is that I will be assuming concentration RES star, that is equals to concentration of K1 concentration of ET, that is E total enzyme concentration, minus K1 concentration of ES star minus K2 concentration of ES star, and minus K3 star concentration of ES star. Why? Because concentration here, concentration of H2O is very high. So from pseudo steady state approximation, K3 concentration of H2O pseudo steady state, that is equals to, I am assuming that is K3 dash, right? I think it's very clear. Now that rate should be equals to zero. So can I write K1 concentration of ET? Sorry, here it was concentration of substrate was there, right? So we'll have to use that part also. Here it will be concentration of ES star into concentration of S. So concentration of S, so that is equals to, if I take concentration of ES star common, so it will be equals to K1 concentration of S plus K2 plus K3 star, right? So from here, can I calculate concentration of ES star? That is equals to K1 total concentration ET concentration of S, and it will get divided by K1 concentration of S, uh, K1 concentration of S plus K2 plus K3 star, right? So from here, can I get ES star, that is equals to concentration of ET concentration of S, and divided by concentration of S plus K2 plus K3 star divided by K1, right? So it's very important for this derivation. So we have calculated the value of that enzyme substrate complex. Okay. So now coming to the rate of subtract minus of Rs, that is equals to K1 concentration of S and concentration of Et minus concentration of Es star minus K2 and concentration of Es star. So can I write that is minus Rs? Now we'll be substituting the value of Es. So can I write K1 concentration of S and that is concentration of Et and minus concentration of Es star, we have calculated K1 concentration of Et concentration of S divided by concentration of S plus K2 plus K3 star and divided by K1, okay, and that will be equals to minus K2 and concentration of Es star, again we'll have to substitute K1 concentration of Et concentration of substrate upon concentration of S plus K2 plus K3 star divided by K1. It looks like very bulky, but I am sure, I am assuring you that it will be very easy when we'll derive at the end. So you don't have to do all these derivations for the GATE examination. I'm letting you to understand how we can derive if you forget the final formula, right? So finally, we can write that minus of Rs, that is equals to K1 K3 star, that is total enzyme concentration Et concentration of S and divided by K1 concentration of S plus K2 plus K3 star. So finally we can write concentration of Rs, that is equals to K3 star concentration of Et concentration of S and divided by concentration of S plus K2 plus K3 star divided by K1. So in both numerator and denominator, I have divided by K1. So from there, I have got this particular formula for rate for the substrate, that our reaction was S plus E getting converted into ES star, that is enzyme substrate complex, and it is getting converted into product plus enzyme. So here that reaction was K1, K2, K3. So our main goal should be, we'll have to understand the significance of all these parameters. So this K1 is rate constant for forward reaction for this particular reaction, that is K2 is a backward rate constant, and that is here it is K3. So I am writing here that is K3 star. Sometimes if nothing is given, that is K3 star is equals to K3. So it is a checkpoint that you should check. But most of the time, sometimes concentration of water used to be neglected in some books, or in some books they don't. Some books don't neglect the concentration of water. That's why I've written that is K3. So don't get confused about it. So now we have calculated the RS. Now uh, coming to different cases for this reactions, right? So if I am writing RS, that is equals to K3 star concentration of Et concentration of S upon that is concentration of substrate plus Km. So I am writing first here, then I will define the value of Km, right? So that is K2 plus K3 star divided by K1. So I am going to define one very important parameter, that is K2 plus K3 star divided by K1, that is called Km, and it's very important parameter, and the name of this parameter is Michaelis Michaelis constant, right? This is very important parameter that you should remember, otherwise you won't be able to solve the problem. So on this particular parameter, uh, question used to be asked. So here we have calculated the rate of this substrate. So can I write here that is minus of Rs, that is equals to K3 star total enzyme concentration, that is substrate concentration upon substrate concentration plus Km. Now case first, Case first, if substrate concentration is very greater than Km. If substrate concentration, I will let you know the units of Km and all. So first try to understand. In case first, if substrate concentration is very less than Km, so can we neglect Km? Yes. So what will be our rate? Rate is equals to K3 star concentration of E total, concentration of S, and if we are neglecting Km, so it will be equals to concentration of S. So this S and this S will get cancelled out, so you will be getting that is K3 star in the concentration of E3. And this parameter is defined as Vmax, and this is called as the maximum rate. Maximum rate. It's very important. What is Vmax? That is the maximum rate. And when it Vmax occurs, when substrate concentration is very greater than this Km. So you'll have to understand this formula only. If you are able to remember this formula, then the thing will be very easy. So in case first, we are getting if substrate concentration is very high as compared to Km, then maximum rate will occur. Now, in case two, try to understand if substrate concentration is very less than Km. If substrate concentration is very less than Km, so concentration of substrate can be neglected. But when we are doing this approximation, then we can neglect with respect to Km, right? So if we our rate is Rs, that is equals to K3 star concentration of E3 Et, that is concentration of S, and here it was concentration of S plus this is Km, this is Michelin constant. So we are neglecting this S with respect to this Km. We cannot neglect this here. This is in the multiplication, right? So it will be equals to 0, I am assuming. So that is equals to A3 star concentration of E3 concentration of S upon divided by Km, right? That is equals to Km. So, and already in the previous slide, I have discussed about that K3 star into concentration of Et, that is equals to our Vmax. K3 star into Et is Vmax. So, can I write that is minus of Rs, that is equals to Vmax into concentration of S upon Km. So these types of question can be asked that different condition will be taken, that I have taken if concentration of ice is less than Km, here we will be getting rate for the substrate formations, substrate that is equals to Vmax into concentration of substrate upon Km. Now next is case third. These three cases very important for this particular problem. So we know that is Rs, that is equals to K3 star concentration of E total concentration of S and divided by uh, concentration of S plus Km, where K3 star into concentration of E total, we have defined it as a parameter, that is Vmax, that is maximum rate, right? That is the maximum rate. So here that is equals to minus RAS, that is equals to Vmax. And so try to understand one very important thing here. If case 3, if Km is equals to concentration of S, what will happen here? So rate will be equals to minus of Rs, that is equals to, can I write that is I am V max into concentration of S and divided by, can I write 2 concentration of S. So this S and concentration of S will get cancelled out. So rate will be equals to V max by 2. So these three uh, uh, parameters, three cases very important. Now coming to the next, how we'll plot the graph. So try to understand, the graph will be minus Rs versus concentration of substrate. So R, the value of Rs, that was equals to K3 star concentration of Et, concentration of S divided by concentration of S plus Km. So it can be also written as V max concentration of S upon concentration of S plus Km. So minus Rs. This is our main equation. So this graph looks like a hyperbola, right? So this graph will be like hyperbola. So you can draw this curve like this, right? So if substrate concentration is very high, if substrate concentration is very high, then what will happen? Km will be neglected, so it will get cancelled out. So we will be getting maximum rate. Okay, that already I have discussed that we will be getting the maximum rate here if substrate concentration is very high. So this is our Vmax, Vmax. And here, if substrate concentration is very high, we can see here the rate is becoming constant over here. Okay, so if rate is becoming constant, that is going to be the independent of substrate concentration. Here, the rate will be independent of substrate concentration. So which kinetics it will follow? It will follow zeroth order kinetics. It's very important. It will follow sorry zeroth order kinetics at higher substrate concentration. Here we can write substrate concentration is very high, right? Now coming to this particular point, when substrate concentration is low, when the substrate concentration is low, then what is the rate? Minus of Rs, that was equals to Vmax into concentration of S by Km. So you can see minus Rs, that is directly proportional to concentration of S, right? Minus Rs, that is directly proportional to concentration of S at lower concentration of the substrate. So it will follow first order kinetics and it will go like that, right? Here it will follow first order kinetics when at low substrate concentration, at low substrate concentration, right? And one very important thing was that uh, uh, when substrate concentration is S is equals to Km, it was also there. When concentration of substrate that is equals to Km, so rate will be equals to what? Rate was, this rate was Vmax by 2. This rate was Vmax by 2. I am again here drawing this uh, curve, so it will be very easy for you to understand. So at substrate concentration is Km, here it is substrate concentration and here it is minus of Rs. So if substrate concentration that is equals to Km, so our rate is equals to Vmax by 2 and here it is Vmax. So here it is Vmax. So you can see here it is following zeroth order, here it is at lower substrate concentration is following the first order. So overall you can see from this graph, if this graph is like that and higher concentration of substrate, here it is higher concentration of substrate and here this on the y-axis this is minus Rs, so it will be Vmax at substrate concentration is Km, that is Michelin constant, so rate will be equals to Vmax by 2. Here sorry, it will follow first order kinetics, here it will follow zeroth order kinetics. So it's very important that you should understand these things here, right? So now coming to the next, that is one very important method for this particular concept is a differential method. Differential method, okay? So we can write that rate, that is 1 upon minus Rs, that is equals to Km by Vmax into substrate concentration plus 1 upon Vmax, right? I'm just writing in the different form of that equations that we have derived earlier. And this equation is very, very important. And this equation is known as line Weber and Burke plot. It has been given in 1934 here, here 1934. So this plot is known as the line Weber plot. So from this plot, you can also get some question here. What types of question you can get? So let's try to understand. If I am drawing that 1 upon minus Rs versus 1 upon substrate concentration S. So this plot will be also a linear plot and having this intercept that it will be equals to 1 upon maximum rate Vmax, right? 1 upon maximum rate, and the slope of this plot that will be equals to Km upon Vmax. So if this plot has been given in the problem, so you can calculate the intercept from here. So intercept will be give you the 1 upon Vmax, and you can calculate the slope, and from there we can calculate this Michelin constant. That is very important parameter. So from here we can calculate Km and Vmax also. So from line Weber plot, we can calculate. So line Weber plot is the plot between 1 upon Rs versus 1 upon S, right? So it was very important. So I am going to discuss about some very important thing about the Kmax, Km, that is Michelin constant. That is Michelin constant. Sometimes in multiple choice question, we can MSQ question, we can get the problem from here. So we can define the value of Km. It is a substrate concentration. It is substrate concentration at which the enzyme operates at half of, sorry, so don't mind about the handwriting, so it's bad, but I'm trying to understand the concept. At one half of its maximum value. So already I have told you, if Km is equals to substrate concentration, then what Rs is equals to Vmax by 2. So this was the definition of K, that is Michelin constant. Sometimes in the problem, if it is in the statement form, you can get the problem from here. No, now, so if an enzyme has a small value of K, so then it will achieve maximum catalytic efficiency, right? So a small value of Km, then it will be showing maximum catalytic. So sometimes in the problem, if some it is giving K1 is equals to 2.5, K2 is equals to Km1, Km2 3.4, and that is Km3 that is equals to 6.5. So which will be working with the maximum efficiency? So Km1 will be working with the maximum efficiency. If this enzyme is E1, if this enzyme is E2, if this enzyme is E3, so E1 will be more efficient as compared to another one. So this was the basics understanding from this particular concepts. Now, a higher value of K signify higher value of Km signify lower affinity, lower affinity. So how you can reduce this from here? I am taking you, letting you to understand with the help of one graph. So the plot will be like that only. So there is three plot. There are three plot here. So I am assuming this one is S1, this one is S2, and this one is S3, right? So the rate will be like that. So here this rate will be Vmax. So how do we get the value of Km? So we used to come from here because here it is Vmax by 2, and where this plot will intersect, so it will be value of Km1. So it will give you the value of Km2, and here it will give the value of Km3, right? So from here you can get Km1 is less than Km2 is less than Km3. So if Km1 is less than Km2 is less than Km3, so which have lower affinity. So S1 has higher affinity as compared to S2 as compared to S3. So while observing the parameter Km, that is initially constant, we can analyze which enzyme substrate reaction will be better or not, right? So that Km value, higher Km value signify that lower affinity of the reactant, right? So hope I have tried my best to let you understand this misalignment and enzyme analytics equations, and have taken three cases for different conditions. Have discussed about the plot. Have also discussed about Lineweaver plot, and which types of numerical can be asked over here. So in the next lecture, I will be discussing about the numerical on this particular topic. Okay. So okay, thank you and all the best.